So the summary of my talk is quite easy. I think you heard of many revolutions. There are revolutions in information technology. You may not have heard about the microwave revolution. It's quite important. And I will particularly emphasize the work which we have been done, Neil and myself, on ceramics and functional dielectrics. The second part is about what we are all looking for after the talk, liquids, drinks. So it's about the microwave investigation of liquids, and actually you can do a lot if you use microwave sensors. You can learn a lot about the properties of liquids, and you can actually use that in practical sensor device. And the third part of my talk is something which you may not expect from microwaves. You can actually build a microscope with microwaves, and with such microscope you can get a completely new insight into materials. And I will show some quite recent results on graphene, which is quite interesting material for microwave and terahertz applications as well. And last but not least, there is even a challenge of microwave related to biology and medicine, and I will address that in the last part of my talk. So if you consider that you are an undergraduate in the fourth year and your professor asks you to write your research project about microwave, the first thing you do, you type microwave into Google. This is really very exciting. So you see what the microwave revolution is about. You've got some fancy combination with toasters. That looks more like advertisement from the early 60s, Happy Housewife. Actually, the student made a mistake. He should have typed in microwaves rather than microwave. And if you type in microwave, it's getting much more exciting. As you can see, you'll see here microwaves for $29.99 from Tesco. But there are things which are more scientific. So if you look at this bit here, for example, you see a proper definition of what is meant by microwave. So we are talking about a part of the electromagnetic spectrum, which from point of view of wavelengths is between a pinpoint and a human, let's say a small child, like my daughter Elisa. So we are talking about wavelengths between millimeter wave and tens of centimeters. In terms of frequency, we are talking about frequencies, let's say, starting at around 100, 200 megahertz and up to, depending on which definition you use, 100 gigahertz to 300 gigahertz. And in terms of temperature of an equivalent blackbody radiator, you are talking about very, very low temperatures. So the blackbody radiation at 3 Kelvin has a center at around 200 gigahertz. And what is important is shown here in the upper part. So when you look at the windows in the atmosphere, where the Earth's atmosphere is transparent for electromagnetic waves, you've got basically two windows. And one window is in the visible range, and that's a quite narrow wavelength regime in comparison to the entire electromagnetic spectrum. And there is a second big window which basically extends from DC up to the millimeter wave range. It gets a little bit into the far infrared range. And, well, that's the reason that humans have the visibility in the visible range, but you can, of course, use the electromagnetic radiation both in the visible range as in the microwave range for communication and remote sensing over longer distances. However, what is also important if you're going to use electromagnetic waves for material spectroscopy is that the absorption and the response of matter is very different for the different frequency ranges. In nature, there are lots of photons in the microwave range around. So you know that Penzias and Wilson discovered the blackbody radiation coming from the Big Bang, corresponding to a blackbody radiator around 3 Kelvin back in 1964. And meanwhile, the spectral distribution has been recorded over a very large frequency range, mostly by satellite experiments. And basically what you know from that is that the 3 background radiation has a peak at around 200 gigahertz. That's somewhat funny. So if you think about how many photons you have in the universe, you find out that the largest number of photons you have indeed between about 100 gigahertz and 1 terahertz, where unfortunately the equipment is most expensive. So we are struggling to get a network analyzer going in this frequency range. It's most expensive, but you've got many photons in nature. There are also all kinds of technical microwave sources, and what most people in the public do not realize, that your mobile phone indeed is a microwave device. So this would be possibly the worst advertisement you could ever do for a mobile phone, because actually the mobile phone emits a power of around 3 watts, and it can potentially even do some damage to your body. It heats up your brain, basically. I mean, it's, let's say, really some risk if it has been too often used for small children, for example. So there has been a lot of historic innovations which finally have led to the breakthrough of microwave, which initiated the microwave revolution. First, of course, there were a couple of World War II innovations, and one important innovation by John Randall and Henry Booth from Birmingham was the development of the cavity klystron. So that's the cavity magnetron. So that's till nowadays the working horse of all the microwave ovens. And this is basically based on an array of cavities. The electron beam held by a magnetic field is moving around and transfers its energy to the cavities, and the microwave signal is coupled out here. The whole thing is usually made from copper. I wonder how they can make a microwave oven for $29.99, keeping in mind the copper price. But that's basically the working horse of all the microwave ovens. And of course, there is let's say, the most important innovation came from microelectronic development. As you all know, nowadays the limits for transistors goes up to higher and higher frequencies. I like to mention just a few materials. Even silicon, the computers now are microwave devices. They work at frequencies 2-3 gigahertz. Silicon, germanium, gallium arsenide, indium phosphide are materials which you can build transistors which work to frequency close to 1 terahertz. And I'm very happy that from autumn on we will have a new lecturer in the department who is dealing with gallium nitride. Gallium nitride is a very important material for high-power microwave electronic, and it's supposed to replace, for example, the tube amplifiers which are still working on satellites for satellite communication. So, and also, it's interesting that quite recently people have managed to build transistor prototypes out of graphene, which work up to frequencies of 100 gigahertz and above. So graphene is possibly one way towards a low-cost electronic which works at quite high frequencies, for example, for a plastic electronics to be used in RFID technology. So what I want to do now, I want to highlight a little bit the work on microwave ceramics. And again, let's use Google. If you type microwave ceramics into Google, then you see all kind of different things. You see, of course, some technical devices, which I will discuss later. There are some dielectric capacitors, dielectric resonators, but there are also some simple ceramic device. And one very simple way how to determine the performance of a microwave ceramic, just by one of those pottery, put it in the microwave oven, switch it on for 5 minutes, and when it feels hot, you know that you have a very bad microwave ceramic. Is it still cold? No? Then the losses of the ceramic is very low. And therefore, the optimization of the ceramics is mainly to how can you make a ceramic which has very, very low losses at microwave frequencies. And at the same time, you really have to understand what are the phenomena which finally lead to microwave absorption of ceramics. And as Neil was mentioning, we had about 3 European projects which were basically about the microwave ceramics. And one project was called DiHi-Mico, which we did from 96 to 99. This was still a combination of high-temperature superconductors and microwave ceramics. But at this time, it was quite important that the substrates on which the high-temperature superconductor films were grown, they were contributing with their dielectric losses to the performance of the devices as well. So for let's say, optimizing the performance of a high-temperature superconductor device, we also had to understand the properties of the substrates, and therefore we had to study the microwave properties of dielectric ceramics, particularly at low temperatures. Foams was already related to what we are doing now in the department with Peter Petrov, who is on this picture as he's still a young guy, but he was younger than that, on a project meeting in Ljubljana, beautiful castle here. And this is about functional oxide thin films, nonlinear dielectric thin films, which can be used to generate tunable microwave devices which are based on the ferroelectric phase transition that you can tune the dielectric properties by means of an applied external electric field. And tough was quite tough. Actually, it was a project which was very much dictated by the demands of industry. That's our colleague from Ericsson who was viewing that we do the right things. And so we had to deliver tunable filters. They were tested at Ericsson, they never came back. But hopefully they may use it or not, we don't know. No? And as you can see here, this picture which I showed at the very beginning, this was taken on one of the conferences about this tunable dielectrics which we had in Switzerland. And you see here Neil, some paparazzi took a photogram. He was secretly training for the Olympics, I think. So, those dielectric ceramics, they are usually prepared in kind of dielectric resonator. And the dielectric resonator you may just imagine as a piece of a dielectric waveguide, like you use in optics, but of course bigger because the wavelengths are longer. And if you choose the right electromagnetic mode, you can excite electromagnetic modes of high quality factor. And the quality factor is kind of figure of merit of those resonators. You would like to compete with metal cavity resonators, which are used in the klystrons I was showing at the very beginning, and you would have a Q factor of at least a couple of thousand, if not 10,000, in order to use that really successfully in telecommunication. And it turns out that the quantity which we are looking for, which we have to understand, which we have to simulate with our theoretical models, is the loss tangent. And the loss tangent is the imaginary part of the complex dielectric function divided by the real part. And that is directly related to the quality factor of the resonator. So if you have a low loss tangent, you can get a high Q. And therefore, single crystalline materials, interesting for substrates, but also polycrystalline materials, they basically define, their properties define whether you can use the material at microwave frequency. So that's one of our early papers, which I think, from which we learned quite a lot about the nature of the losses in the ceramics later on. So these are single crystals of lanthanum aluminate. At this time, it was one of the most important substrates for high-temperature superconductors, which were operating at around 80 Kelvin. And as you can see here, there was a peak in the losses, which we couldn't understand. So therefore, within one of those projects we did, together with Niels group, a systematic study, theoretically modeling in terms of quantum phonon processes, in terms of Debye relaxation, in order to get a better understanding of the losses. And what we found out, even if you have an almost perfect single crystals, you've got some losses which are beyond the intrinsic losses, which are unavoidable by the phonon systems, which are indicated by the dotted lines. And these defects, actually, we found were due to atoms on interstitial lattice positions. We found that aluminium atoms on interstitial lattice positions, even if the concentration is very low, can give rise to a loss peak which, from its temperature dependence, basically can be explained in terms of a Debye model. So actually, this paper's got a quite remarkable number of citations, keeping in mind that the community was very small. So half of them are sitting here in this Kuba-style bar in Warsaw, where we had one of our project meetings, and you see a lot of known faces. Peter Petrov here, I think, is here. I think after that he decided to spend his holidays in Cuba. And also, at the same time, we had projects with industry where we even thought that cryogenic dielectrics may be an interesting option to improve the properties of telecommunication systems. And this is work we did together with Bosch Telekom in Germany, which is now belonging to EADS. And that's basically a novel type of dielectric filter which we designed, and I think which got a record value in extremely low insertion loss. Extremely low insertion loss is important if you operate this filter in the output multiplexer of a satellite. You basically save microwave power, and that means since the power amplifiers do not have 100% efficiency, you save payload. So it was the idea, if you can put a cryogenic platform on the satellites, which may include cryogenic dielectric devices, but also high-temperature superconducting devices, you can increase the performance, and at the same time, even if you take the cryocooler into your energy balance, you may benefit in terms of payload. This was a space qualified experiments which we designed at that time, which even passed all this rattling and shaking experiments. Unfortunately, it did not for cost reasons, it was not finally launched. It was supposed to go on the IMS, International Space Station, on the ISS, but unfortunately it didn't happen. And then it happened that for cost reasons, whatever reasons, the company stepped back from using cryogenic in space and concentrated more on the properties at room temperature. So therefore, we were then, from that time on, we more were interested in optimizing and understanding the losses in dielectrics at room temperature. And that's just an example which shows that if you have a single crystals of aluminum oxide or of titanium dioxide, you really get an almost perfect behavior where the losses are entirely determined by phonons. And that's very interesting because the loss tangent at cryogenic temperatures goes down to 10 to the minus 6, even 10 to the minus 8. And at NPL, for example, they use cryogenic dielectric resonators successfully to build frequency standards. Not rutile, but aluminum oxide, they can get Q values up to 10 to the 9, which is, apart from the cesium standards, one of the best frequency standards, which even has a better short-term stability than an atomic clock can have. And even people now work on combinations of atomic clocks and this passive microwave frequency standards. This is basically the result of a long story of optimization of microwave ceramics. So one of the substances is called BMT, barium magnesium tantalate, a very highly ordered, well-sintered ceramic, which apparently gets loss tangent values in the range of 10 to the minus 5, which are almost as good as you can achieve in a single crystal. However, it's still, the temperature dependencies are still somehow not really understood. They were not really understood because the effect of the grain boundaries were not very clear. And at this point, I would like to give reference to a very exciting experiment which has been done by Jonathan Breeze and Neil Alford in this group here just a couple of years ago. They wanted to find out what is the effect of one grain boundary on the microwave losses. So because we knew by comparison of ceramics and single crystal that the ceramics always have slightly higher losses, you have to increase the grain size in order to get the best performance of the material. But even then, if you have the best material, you are still slightly above the losses in the single crystal. And they did a very exciting experiment. They built a spherical dielectric resonator, which is shown here in a metal cavity excited by coupling loops. And then you get here the field distribution of the so-called TE01 delta mode. And as you can see, due to the spherical symmetry, this mode is threefold degenerated. So you can excite it either with the electric field in plane or out of plane with the grain boundary. And what they found is very interesting. Even if you have an almost perfect grain boundary here, which is shown here in the TEM picture, which has been measured in David McComb's group here in the department. Even then, you get a peak, a relaxation peak, very similar to what we observed years ago in lanthanum aluminate, indicating that even a perfect grain boundary already can significantly contribute to the microwave losses. In other words, you can even say that the measurement of the dielectric losses at low temperature is a kind of interesting spectroscopy in order to learn about the properties of grain boundaries. And what was the conclusion of this paper, which was published just 2 years ago, is that even oxygen vacancies in the vicinity of the grain boundaries may lead to some Debye relaxation process, can move around. And since you have these extremely low background losses in the crystal at cryogenic temperatures, you are able to see these very, very small effects, even if you just have one grain boundary going through the entire crystal. And that indicates something which is very important also from point of view of applications, that microwave measurements have the advantage they are extremely precise. So you can, with a microwave resonator, whatever you measure, liquid, whatever, you can always get a very, very high accuracy because resonators, dielectric resonators can have a very high Q factor and they therefore are a very, very nice laboratory for doing all kinds of measurements on substances which you have in very small volumes, for example, like biomolecules, and you will see some results in the rest of my talk. So as I was telling you that the current focus of our work on dielectric materials in the department is very much driven by thin films for good reasons. First of all is that the properties of the dielectric bulk ceramics are quite well understood, but also from applicational point of view, there is a strong demand for building tunable devices. Why is that? Because in telecommunication, you have to do with a very narrow and expensive bandwidth. You remember when the UMTS licenses were sold years ago. The companies like Vodafone, they paid billions of euros or pounds for this very small 5 megahertz frequency intervals, which is allocated. So therefore, what you would like to do in order to have a perfect utilization of the frequency bands, you would like to have a reconfigurable microwave device. You would like to have a filter which you can drive electrically from one end of the frequency band to another in order to deal with the changing demand of bandwidth and the changing uplink and downlink data rate capability. And as a kind of replacement for the semiconductor varactors, it turns out that a mixture of barium-strontium titanate, a ferroelectric material, but with a ferroelectric temperature slightly below room temperature, you can get a very, very strong change of the dielectric constant at an applied voltage. Tuning factors, in this case 15%, were achieved. But one problem was, because you have a mixed tachometry, you don't have this highly ordered system like you have in barium-magnesium tantalate. Therefore, the dielectric losses are very high because you have charge defects. So, and what Peter and others did, and I think that's an excellent approach, they just were mimicking this tachometry by a multilayer of barium titanate and strontium titanate. And electrically, they get very similar properties. They got tunability of the same order of magnitude, but at lower losses because they are dealing basically with more perfect crystalline layers. And at the same time, they even got an advantage that the temperature dependence of the permittivity is much smaller. And that's a very important thing because if you would like to operate your device, you have certain specifications that the device has to operate between minus 30 plus 70 degrees. And if the temperature dependence of your ferroelectric is running out of range, you can't use this device for any application. So therefore, that's an extremely important thing with respect to applications. And actually, the interesting thing, what even makes it interesting for the future, we found in a work which we did together with a group at the Institute of Physics at the Academy of Prague in Czech Republic, we found that ferroelectric films can even be used up to terahertz frequencies. And what we did was a kind of interesting experiment. We took a film of strontium titanate on a sapphire substrate, and then we were basically preparing a kind of interdigited capacitance where you can apply a voltage across a film, but at the same time, we use this interdigited capacitance as a polarizer for a plane wave which hits onto the sample in this direction with the polarization vector pointing in this direction. And basically you got a wire grid polarizer. The wire grid polarizer turned out to have a transmission of above 90%. And when you apply a voltage here, you can basically tune the phase. And actually this is a quite nice device because it can, on the one hand, it allows to determine the voltage dependence on the dielectric constant. And you see we got a tuning range up to almost 1 terahertz of about 10% in this case. And at the same time, it's already a device because it can be used as a quasi-optical phase shifter for the terahertz frequency range. So that's all which I wanted to say about our work on the oxide material. So I think it's still going on. We just go together with the colleagues from NPL with Marcus Kane for another EU proposal where Paul Tenge is involved, where we try to simulate the dielectric losses because many of the features in the thin films are not understood. There are a lot of strain dependencies, all kind of things, and I think our feeling is we need a lot of theoretical work to be done in order to get a better understanding what is really going on if we want to go further ahead with getting better performance out of those oxide multilayers. And I think, in my opinion, it's very challenging to go further towards the millimeter wave frequency range because at low gigahertz frequencies, the semiconductor varactor is doing well, but as you all know, the semiconductors are getting quite lossy, and therefore I think the higher the frequency is, and also for high power applications, the ferroelectric varactors, they really have a quite high potential. The second part of my talk basically came from the kind of drive to go towards application. I mean, since we have this very high Q dielectric resonators, we thought, is there anything useful we can do with that, apart from using them for studying the losses in the dielectric material itself? And one of the focuses we had was on liquids. So why are liquids interesting for microwaves? You all know when you put a glass of water in a microwave oven, it heats up very quickly. So obviously there is a strong absorption in the microwave regime. And basically, this can be easily measured. So we've got a kit in our laboratory, which is a kind of coaxial probe, which works very easily. You connect it to a network analyzer, and then basically it records what is called the complex dielectric permittivity of the liquid. And this is a plot which has been measured by one of my PhD students. It basically shows the real part of the dielectric constant as a function of frequency from about 100 megahertz up to about 20 gigahertz, and it shows the imaginary part. And what you see at low temperature, you have a constant dielectric constant. The reason is that the process which defines the dielectric losses, the dielectric properties of water, is the orientational polarization of the water dipole molecules, and that's a quite slow process. So every time when you change the phase of your microwave signal, the molecules have to move around, and this goes typically at relaxation speeds of the order of a couple of picoseconds. That means if your frequency exceeds 1/8 picoseconds, it happens that you get a debye relaxation behavior, the dielectric permittivity goes down, and the imaginary part of the dielectric constant, which is related to the losses, goes up. You're, of course, in a regime where the losses are about 3 orders of magnitude higher than the losses you have in a ceramic. So water has very high temperature-dependent losses, and the interesting thing in order to really study liquids is that the whole thing can be described by a very, very simple formula. So usually you've got just one debye term. Here I've plotted n debye terms. Some liquids have more than one, but usually just one debye term is sufficient to describe a liquid. So basically you've got the value of the static permittivity, you've got the value of your relaxation time, and that's it. So basically 2 values. There is even a permittivity at higher frequencies, but that's not that important. These 2 parameters basically allow you to describe a liquid. Now you may ask, what happens if you look at mixtures? And one of the most interesting mixtures is, of course, the water-alcohol mixture. And what you see there is that the dielectric constant drops. So the static dielectric constant drops. That's not surprising because the polarizability of the water molecule is much higher than the polarizability of the ethanol molecule. It's a semipolar liquid. But at the same time, you see, basically due to the fact that the water molecule has a higher mass and a higher inertia than the alcohol, than the water, then you get a reduction in the relaxation time as well. And the relaxation time goes to lower frequencies. Actually, if you look for a set of different liquids like methanol, ethanol, propanol, you see that all the liquids show very simple spectra. Most of liquids just show 1 or 2 debye relaxation spectra, but their values of static permittivity and relaxation time differs very much. And that's important for any experiment related to the identification and concentration determination of liquid, that basically the microwave spectrum allows a kind of fingerprint detection of a liquid. So therefore, we have identified another possible area of applications. And the question is, can you use that, for example, for biosensing? In any biological liquids in the human tissue, you have many, many hundreds and thousands of different proteins and molecules being present. And you would like to sort out what kind of concentrations you have, what kind of molecules you have. The question is, can you build a biosensor which is based on dielectric spectroscopy? And this is just something which we study within a running thesis project. And the student, Toby Fischer, he has basically started to study with very simple molecules like methanol, more complex like glucose, and then he was looking for different proteins. And now he's starting to work on virus replacement molecules like nanospheres, which are coated with peptides. And he would like to study what happens if you mix them in water, not at very high concentration levels. Usually in biological liquids, you have them at very low concentration levels. So you would like to know, can you differentiate between these solutes just by measuring the complex dielectric permittivity in the microwave range? And actually, it works surprisingly well. So that's a little bit crowded view graph. But what it shows, that those four substances show a completely different but linear dependence of the Debye parameters, the static permittivity, the relaxation time, and the conductivity as well on the concentration. So what does it mean? If you are in this linear regime of concentration, and if you've got different slopes for the three parameters, you can present that in this kind of 3D plot, and then you can make one characteristic line for one substances. So basically, if you can, provided that your temperature is controlled to a very high extent, and provided that you are able to have sufficient high accuracy to get your measurements done, to measure your frequency and phase as accurate as you can basically determine even mixtures. You can be very selective. Even if you would have a combination of two different substances, you would be able to sort that out. So that's a quite promising result, and we're going to extend that to real biomolecules, viruses, to see whether we can use that potentially as a new method which may allow to have not only a marker-free, but also an immobilization-free type of biosensing. Because nowadays in biosensing, you always have to immobilize your molecules on the surface, but maybe you can just sort it out by doing a measurement on the liquid and try to measure the dielectric parameters as exact as you even can do that. And one important point which is related to this machine, which you may have already recognized here, which I may switch on now. When you look at the Debye relaxation formula, you basically have three parameters, or you've got four. In reality, you've got epsilon infinity, static permittivity, relaxation time, and you've got the conductivity, which I have neglected so far, but which is important for the identification of liquid. That means if you do a measurement just at two frequencies, you measure the real and the imaginary part of the permittivity at two frequencies, you're basically able to get the whole curve. That means the good thing about the microwave measurement is you do not need to have the whole spectrum. So basically you can take a resonator, operate the resonator at two frequencies, which you can do with tremendously high sensitivity, and then you're able to get the information on the Debye parameters, which basically allows you to a high extent to identify or even to measure the concentration in the liquids. So that has brought us to the idea of using microwave resonator technology for a bottle scanner. As Neil was mentioning in his introduction, there is a strong demand for security applications to go for a safe and fast identification of liquids in a bottle. And one way to do that is take what is called an open or a semi-open resonator, which can be, for example, a dielectric resonator, where an evanescent field, a kind of leakage field, non-radiative leakage field, is leaking through the aperture in the resonator, through the wall, into the liquid. And just you record then the change in frequency and the change in Q factor, which is induced by the liquid here. And then basically, if you sort that out, you can get information about the real and the imaginary part of the liquid in the bottle. So one very easy way to do that is using the standard configuration of the TO1 delta mode in a dielectric resonator. So if you use a piece of low-loss ceramic and put that in a semi-open cavity, then you've got your non-radiating evanescent field here. The Q factor actually is very high in spite of the semi-open configuration, because the evanescent field is non-radiative and the size of the aperture is usually very well below the wavelength. So basically what you do in this bottle experiments, you put your bottle and then you measure the Q shift, and then you're able to determine the properties of the liquid. Interestingly, you can play around with the geometry of the resonators. That's just one example, something which we did recently. We were looking for the dielectric resonator mode in a disk configuration, which is interesting because if you choose the parameters correctly, the leakage volume of the electromagnetic field can be very high. We use this now in a study by DSTL in order to think about whether we can use a dielectric resonator for the detection of improvised explosive devices hidden in the ground. So basically doing some dielectric measurements on objects which are possibly 10, 20 centimeters below ground. So it's just a matter of geometry, but you need the high Q resonator, and then you can even get information. You can sample information from a depth which is of the order of 10, 20 centimeters. Oops. So in the TO1 delta mode, we found that already this single frequency allows for a quite simple differentiation between, let's say, aqueous liquids. So there is a range for aqueous liquid if you plot the frequency shift as a function of the quality factor shift. If you take both quantities, then you find a quite narrow range which allows you to separate the, let's say, normal consumer liquids from most of the inflammable liquids and most of the ionic liquids. If you, for example, take a strong acid like hydrochloric acid, you would get points in this area here. And if you use, say, for example, ethanol, methanol, they would all be in the semipolar area. So this was the first attempt to build a bottle scanner, very simple, very primitive, and but based on that, integrating a kind of low-cost microwave network analyzer unit, which we developed with one of our industry partners who are here in this room, we were able to build a prototype of a one-channel bottle scanner, and this was here in a 2-month test at Prague International Airports. It worked very well in terms of handling, but we found that actually the one mode, which gives only one point on the Debye curve, is not sufficient to really distinguish between all the possible benign and all the possible Schreck liquids, which the regulators would like us to detect. So therefore, we went a step further and said, can we not implement 2 modes in one resonator? And there we came up with a quite clever design, which, as you will see later, we will also use in our microwave microscope in a very similar way. So what we did, we integrated a dielectric resonator in a metal housing with a conventional LC resonator, which works at a much lower frequency. So basically, we put the dielectric resonator on a metal plate, and the metal plate was separated again by a low-loss aluminium oxide ceramic to form a capacitor. And then we had a kind of inductive shunt between the central conductor, which supports the dielectric resonator, and the wall. And in this way, we were able to build a resonator which has one mode operating at 2 gigahertz and a second mode which operates at 100 megahertz. At 100 megahertz, actually the loss contribution of the ions in the liquid is much higher than the loss contribution due to the relaxation of water. And basically, you see that if you take this resonator, that's the resonator how it is, how it looks like. And if you plot the inverse quality factor, for example, as a function of concentration in a sodium chloride volume, then you see that you can determine the conductivity of the solution over a very, very high dynamic range, which goes from distilled water up to the strongest acid. And that's, as far as I know, the only contact-free method which allows to determine the conductivity of liquids through the bottle wall. It's a very important method, I think, for chemical processing, for example. It can also be used for other materials. We've used it for graphene to determine the conductivity in graphene films. We use it for semiconductors. It can be used to determine the conductivity of high-resistive silicon and so far. So it's quite universal technique. And that's basically the unit which I would like to show you. So that's our bottle scanner. And I thought it may be quite relaxing to have a little break at this point and give you a demonstration of how it works. So let me just say the principle is illustrated here on the next view graph. So basically the resonator, the dual mode resonator, measures the response in 2 channels. So we have one channel at 2 gigahertz and another channel at 100 megahertz, and then you get a kind of 2-dimensional landscape. So where you basically have the dielectric constant on this axis, and you've got the ionic conductivity on the other axis. It's a bit more complicated because you have a combination of real and imaginary part, but then you can basically define some reject windows where you may have, I mean, that's just a kind of abbreviation for some of the most common liquid explosives, which we know is just a code, so I'm not allowed to tell it to you. But basically, you have all those bad guys here in these boxes, and the black points are a representative list of benign items. So these are basically 500 representative bottles which have been selected from various airports throughout Europe, and they give a kind of broad spectrum. And you see, in spite that there is some overlap between, so we've got some false alarms. There is most of the liquids, the consumer liquids, in all the different kinds of bottles, they are quite well separated from the threat items. And I would like to give you some demonstration, and maybe would be nice to have some assistance. Anna, could you possibly just, we would like now to give a kind of demonstration of a checkpoint. And I don't know, can you see here what is written on the monitor? So that's very simple to use. So basically you see here the shape of the bottle, and that's, I just give you a demonstration. So basically you take the bottle as it is and put it on, and then it gives the results right away. It says pass, because it's a kind of benign item. No? So now we've prepared some really thread items, and this methanol. So just do it from there, no? Otherwise you may, and just try not to stand in front of the mirror, in front of the screen. So it recognizes that it's methanol, no? And then I've got here something. By the way, there is another interesting application, and we've done some preliminary tests at Heathrow Airport. It can detect liquid drugs. So I bought a bottle of liquid ecstasy from the dealer next door. And can you put this bottle of liquid? It's very poisonous, but can you put that on the machine? Let's see what it tells. I mean, that's now what it would tell to a passenger in the airport. Hopefully there's nobody from Holland here. It's always this kind of joke between German and Dutch, so therefore they know that I'm German, and they may understand that. No? And that's really the very dangerous thing. That's hydrogen peroxide. So take care, it's explosive. No? So if you put that on the machine, let's see what happens. Okay, it has also different purposes. Well, I mean, now you may say this is just a kind of fake. No? So what I did, I was confiscating one bottle which I found today in one of the postgraduates' write-up rooms. No? Somebody has removed the label. No? What do you think? It's a whiskey, could be. No? Shall we try? Is David McComb here? Let's see what it says. Yeah, so well, okay, so thanks very much for the demonstration. I hope it shows that this is really a very versatile instrument, and the microwave method is, among of all our competitors, it's really one of the fastest way of proceeding. So therefore, for us, the next step in this business, which is of course a kind of combined industry academic business, we have a lot of things, and one is, of course, we are now currently heading for the European certification to get the system being run in airports. And we're also having some discussion about combining the microwave technology with X-ray technology. We are just talking with one of the X-ray manufacturers in this country, because an orthogonal approach, combining X-ray with microwave, would possibly reduce the false alarm to a large extent, because we still get something like 5–10% false alarms. The X-ray got even more. So if you would combine that, because we've got different false alarms, the total false alarm rate of a combined system may possibly well below 1%. And we are working on other things like IED detection, handheld shoe scanning devices. And also we did a little bit of work here with my undergraduate students on the integration of such system in the airport. And I was supervising this year a design study project, which apparently was quite remarkable. You see the names of the students, they're sitting in the audience here, and they came up with an idea to use RFID technology in combination with advanced screening devices like terahertz scanning, like X-ray, and our bottle scanner, to build a checkpoint which is much, much faster and has a much higher throughput than any other possible checkpoints. And I would like to show you, because it's remarkable what the students found out. And they had a kind of fictive system where basically every passenger's got an RFID tag on his boarding card, but also an RFID tag on the hand luggage. And by this you can basically control, or you can correlate the passenger to his hand luggage. So the passenger just goes through the system, and then he goes to a gate which he can open with his RFID card, and then the door opens, and then he gets into an area where they use passive terahertz imaging in order to get a picture of the person, and then you use a shoe scanner. And then when you go further on, then basically, so the inspector basically controls both the hand luggage as a person, and he can correlate it because everything is connected by RFID technology. And then when he is suspicious, then he can be, of course, inspected in the conventional way. The policeman with the handcuffs is standing along, and then after passing through that, the students found out that this is a factor of 2 faster than conventional checkpoints, just by using existing and possibly already technologies which are a little bit beyond the standard. It should be possible to combine RFID, again, in microwave technology to get definitely a much higher throughput. I found this very remarkable, so therefore I thought it maybe would be worth to show it once here. So the microwave microscope. We thought about if the resonators are so successful for material identification and detection, can we also use that on the microscopic scale? So can we not use a resonator and somehow find a way to focus the microwave radiation down to a spot of micron or less, and then still get a high sensitivity for getting information on the complex dielectric constant of a material? And one of the most important work in this area has been done by our direct colleagues, Andrew Gregory, Bob Clark at NPL. And what they did, they again used our dielectric resonator. So the dielectric resonator is everywhere, but in this time excited in a TM mode where the electric field is aligned with the axis. And then basically they coupled the field of the dielectric resonator to a little miniaturized antenna. And on top of these antennas, they have a small fancy metal probe, which is 100 micrometer, even smaller. And this little probe is moved around like in an atomic force microscope with a little tuning fork. And that's basically what you do. If you approach a sample to this resonator, then you get an interaction between the tip and the tuning fork, which in turn changes the resonant frequency and the Q factor. So just by scanning your sample over the surface of this tip and recording the resonant frequency and the Q factor as a function of the position, you're able to map the dielectric properties of the sample. And that's basically the setup they use. So that's all kind of well-advanced XYZ stage driven by piezoelectric, where you can move around the sample above the resonator. Everything has to be in a sound-protected environment because it's quite sensitive to any vibration. But I mean, after some years of work, they finally managed to bring this machine to a very high level of performance. So, and also they worked very hard to get the proper calibration. So I mean, this is just an example. I mean, they were looking for minerals, for example, and they had minerals which were embedded in plastic. And basically what they can map here is really the spatial distribution of the dielectric permittivity and compare that to other properties. So it really allows to get images of the dielectric constant with a resolution of the order of a few micrometer only. That's very exciting also potentially, as you will see later, for possible applications in biology. We were interested in graphene. You know that we make graphene films in the department. Mani Showala, who was here for 1 year, he basically established the graphene technology. Cecilia Matevi, she's now routinely making graphene films of very, very high performance. And one of the difficulties was they're quite straightforward to make, I have to say, but they're very difficult to characterize. So can we not use a kind of modified near-field microscope, microwave near-field microscope to basically determine the conductivity or the field resistance distribution of graphene? And if you try that with the setup here, you find out it's not sensitive enough. And the reason is that if you treat a graphene layer as a dielectric material, you find out, if you do the analysis of the formulas, if you go into the mathematics, that you have to go at a lower frequency. So if you do that at gigahertz frequencies, you will not be able to see this very, very thin semiconductor layer of graphene, which is just 0.3 nanometer thick. So therefore we thought, can we not build a resonator and combine that with a microscope which has a high Q, but works at a much lower frequency? And that is what Andrew Gregory and myself have just done over the last, I have to say, couple of months. So basically we used a very similar design as we had in the bottle scanner. So we had so-called reentrant resonator, and that's basically a LC resonator, which is a coaxial system where basically the little metal probe is connected to the capacitor plate and leaks through a little hole through the outer environment. And what you see here in the simulation what you see in the simulations that you get a quite high electric field at the tip. And since this antenna is very small in comparison to the wavelengths, you basically do not have any compromise on the Q. Actually, the Q of the system was found to be 3,500, and it's basically not affected by the radiation coming from this little tip. However, if you put, again, your sample, your graphene film, close to this tip, then you might expect a slight modification of your quality factor if the Q factor of the system is high enough. So, I mean, can you imagine that you have one monolayer of graphene brought to this little tip? Would have any effect on the Q factor of this resonator? And the result is quite surprising. So the first thing which we did were samples which I would not even consider as graphene, but they are called reduced graphene oxide. So it's actually quite difficult to make graphene, but it's easy to make graphene oxide. And if you reduce graphene oxide in hydrogen, you can basically get it into a kind of conducting state, but you've got many defects. You've got a lot of OH bonds in the material. And so therefore, it's extremely difficult to get high performance graphene by this way of reduction of graphene oxide. So anyway, we were looking at 20 nanometer thick films of graphene oxide, reduced graphene oxide, which is still let's say a factor of 100 times thicker than a monolayer. And not surprisingly, we found that there is a quite strong reduction even for the mode at higher frequency. So the mode at a frequency of 2 gigahertz showed a reduction of the quality factor from 1400 to 1380, not that much. But there is an effect, and even you can see here that on a scale of 1 by 1 millimeter, it's possible basically to monitor the feed resistance of this reduced graphene oxide. But what you see already here, that if you do the same measurement at a frequency of 280, the Q reduction is much bigger. It goes from 3,400 to almost 1,000. So you see, it really has an enormous effect of sensitivity when you have a high Q resonator operating at low frequency. And I have to say, quite recently, we got really one of the, I would say, world-class thin films from Cecilia Mattevi. So she uses a process where she deposits graphene on copper, which is a kind of CVD process, and this single layer grows catalytically, and it can be transferred in a quite sophisticated way on a dielectric substrate like quartz. And if you do that with a 3 gigahertz resonator, you basically don't see any effect in the Q. If you do that with the 200 megahertz resonator, you see, if you scan over just 0.1 times 0.1, and that's just a very recent result from Andy. So we just got the sample, and we are very, very happy that we are able to basically get this result. And you see here the Q goes down from 3,400 to a value which varies only between 2,300 to 2,600, which means even the homogeneity of this film seems to be quite good. No? So we have not yet done the calibration. This would require some simulation measurements. I think Andrew is working on that. But what I did, I simply did some back-of-the-envelope estimation and compared the reduced graphene oxide with the graphene. And if I just follow my simple model from perturbation theory, that's a change of the Q factor, of the inverse Q factor, in which is induced by the sample, is proportional to the thickness times the conductivity. You find out that the graphene conductivity is about 27 times higher than the reduced graphene oxide conductivity, and this roughly corresponds to what you also get from macroscopic measurements by contact pads. So it seems to be that the averaging over the sample gives the right results. And also, if you take the spread here, you come up to 45% spread between the darkest and the lightest point, and you get to 200% in the reduced graphene oxide, really indicating that the CVD graphene is definitely much better than the reduced graphene oxide. But I mean, we are quite proud of this result, I have to say, because this is in my opinion, the first time in the literature that people observe in a contact-free way the spatial distribution of the conductivity of a single graphene layer. And we think that puts us in a quite good position in the graphene community here in this country, because that's what the people are looking for, to have a tool which really tells you about the properties, resolves that on a microscopic scales. I don't know whether it's possible to potentially get the resolution down to the spatial resolution down below 1 micron. That's, of course, what all people are looking for, because they would like to correlate these conductivity scans with the morphological and structural properties of the material. But let's see, I think we can still do some improvement the near field. Actually, that's, I have to say, one of the European projects which Bob Clark from NPL was organizing. That's a kind of project within the so-called EMRP call, which is a project which is a funding scheme where the standard labs are involved, and we are involved by Imperial College with the so-called Research Excellence grants, with one of my postdocs will take over in some time from now. So, but we haven't yet started the project, but we have already some quite promising results, I think. So finally, if I still have, I'm already almost running out of time, so let me do that very, very quickly, the biochemical challenge towards a terahertz biochip. So is there any medical, biological application of microwave resonators and microwave or terahertz technology? And that's it here. So microwave doctors. This was a kind of first clinical study we did about 2 years ago. That's two of my colleagues from Prague, Center for Hemodialysis in Czech Republic, where we came up with the idea, can we not use a resonator for monitoring the amount of extracellular liquids in the body during dialysis? So basically what you see is really we went around, here are the resonators, they're hanging here, and we go to the patients and put them on their body. And you see here, that's the way how we did it. No? So we marked one point on the skin and try to keep the arm in a constant position, that the blood pressure doesn't change too much because the microwave technology cannot between the liquid in the blood vessels and the extracellular liquids. And we got some quite nice correlation. So if you do this measurement during the dialysis and plot the frequency shift of the resonator as a function of the removed liquids you see, you get a correlation. That's still in progress. It's still the statistics is not that good at the moment. We have to think about to measure at more than one reference position to get that sorted out. But potentially it could be used for dehydration assessment in emergency medicine, but it could also be used as a kind of self-assessment methods, because more and more people do home dialysis, and if they would have a kind of objective way how to measure the liquid content in their body, it would be useful. But I mean, it's a matter of choosing the right evanescent field with the right penetrations and selecting the right part of the body where the influence of the blood vessels isn't too big. No? Just very quickly, we did some scans also with a similar microscope back in Jülich 3 years ago on dental tissue. Again, the water content. The water content can be mapped here with a resolution of about 20-30 micrometer. That's quite interesting to use the microscope at NPL for biological sample, because if you've got 1 micrometer resolution, you may be able to determine the biorelaxation parameter, to scan them, to map them for cells and see what is going on in different cells. I mean, is there a difference when you cross the cell membrane and so on? So I think it's quite challenging, and even to extend it up to terahertz frequencies. What you see here basically is you can, for example, identify granulated tissue, which is a kind of pre-periodontitis stadium, just by a slightly higher water content, which you can visualize by microwave measurement. Similar studies have been done here in the UK by terahertz spectroscopy, but you can do that nicely with microwave. Just a few quick words. Biosensing. I told you at the very beginning that you can investigate biological liquids, but for this dielectric probes for doing spectroscopy, you usually need 10 milliliters. Can you not do the same thing at nanoliter? And what we used is a mode in a dielectric resonator which is called the whispering gallery mode. And you all know the whispering gallery. It's in pulse-cathedral. Basically, these are modes in dielectric resonators where the electromagnetic field goes around by total reflection. The Q factor is extremely high because there's no radiation leaking out. And if you do that with a sapphire resonator, you can get a Q factor of 100,000 at room temperature, 10 to the 9 at cryogenic temperature. So if you spot now a little droplet of water on that at a maximum of the field distribution, you basically see that you get a reduction in Q just by something like 100 picoliter. And if you do that in a systematic way, you're able even to do concentration measurements on very small amounts of liquids. And that's basically what we are going to do next to investigate a microfluidic system by using resonators at various frequencies to basically reconstruct the total debye curve at some points in a microfluidic environment where you just have nanoliters of picoliters volume. So one of the projects which we actually are planning to do with my colleague Stepan Lucic, he's on a sabbatical in Japan now. I mean, in electrical, well, Eric Jakeman is here. He could talk more about that. They've got the silicon micromachining technology, although I was saying that silicon is a very bad microwave material at low frequencies. But when you go to very high frequencies, to millimeter wave, it happens that silicon is actually very good because the effect of the free carriers is going down. So what you can do, you could basically make these whispering gallery mode resonators on an integrated chip design, an integrated microfluidic channel. So you could really develop this work towards what I would call a terahertz biochip. Alternatively, since we work with Stefan Meyer and John Pendery, we thought about, can we not use this kind of unconventional resonance structures for the same purpose? So can we not, rather than using a classical dielectric resonator, can we not go to more advanced structures? And one interesting possibility, which we just have done the first simulations, is using what is called a photonic bandcap structure. You know, photonic bandcaps came already around 10, 15 years ago, but I think they're still interesting, and not many experiments have been done in the millimeter wave range. But what has been shown and now being reproduced by ourselves is that you can make defect resonances in dielectric slabs. So basically, you can confine modes in a very, very small volumes just by Bragg reflection in a periodic array of holes and combination of total reflection in the third dimension. And if you would combine that with a microfluidic channel, you would get a very, very high sensitivity for measuring very small amount of liquids. So, and another project is going on with Stephen Hannam, who is working with me and with Stefan Meyer. So we try to think about using plasmonic structures. You know, plasmonic structures are very well known in optics. You can take gold nanospheres, but they don't work very well at microwave frequencies because the plasma frequency is in the optical range. But if you take an undoped semiconductor, like indium antimonide, you can reduce the charge carrier to an amount that the plasma frequency is around 1 to terahertz. What does it mean? You can basically make something similar to nanospheres, but these are microdiscs, let's say 10, 20 micrometer diameter, and you can generate electromagnetic mode, plasmonic modes which move around the microsphere. So John Pendery came up with a very interesting idea, which is called the kissing disk. He could explain it better than me. So basically, you take two of those spheres, put them very close together, and then you can even concentrate your fields in between to a very, very large amount. And since the wavelength of this plasmonic wavelength is getting very, very short, you can excite a very high number of modes over a frequency interval. Basically, the system would allow you to do even quasi-broadband spectroscopy at terahertz frequency on a volume which is definitely much, much smaller than the wavelengths. And the simulation are very interesting. We are working with IMRI in Singapore, and we've got the first samples. Results are not bad, so we just got these structures, the first kissing disks, where they really try to use e-beam lithography to get the distance down to 100 nanometer or less. And I'm really looking forward what the results will be. So I think that's a very challenging development. And finally, we will see which technique is most suitable for the bio application. So, well, that's basically the end of my talk. And rather than giving a conclusion, I would like to show it's a kind of bit of fun, so don't take it too serious. It's a kind of little movie which I found in the internet, which is basically based on a vision which came from Dr. Martin Cooper from Motorola, who was one of the pioneers in telecommunication. And you see he had a most advanced smartphone where he did proudly presents to the public the first analog talk, which was really a kind of sensational thing at the time, back in 1973. And let's see whether this works. It's really funny, so that's I think a good. An error occurred. Now that's of course try again later, so it's blocked now. Sorry, I can't show that. So that's a kind of Swedish cartoon which basically shows the conversation between two guys. One had the telephone chip implemented in his finger, the other in his tongue, and they do a kind of funny conversation. Sorry that I could not show that, but I mean, you may write down this link and have a look on your own. It's lots of fun, actually. No? Okay, so I very, very much like to thank you for your patience. I realize that I have already talked too long, longer than I should, and I would really like to address my thanks to a couple of people. Some of them I would really like to mention explicitly. First of all, thanks to Katie and Sonia for doing a perfect organization, and I'm pretty sure that we will have an excellent opportunity to have a drink and discuss a little bit further on through the evening. And also very explicitly, I would like to thank my PhD and research students. Without them, I would not have all these results. So it's always most of the effort is by the work of young people, and PDRAs as well, Stephen Hannam and Cecilia and so on. And also my friend and colleagues from NPL, John Gallup, Ling Hao, whom I know for a very, very long time, and Andy, Kevin Lee. So I think we have an excellent relation with NPL, and I'm really very happy that these collaboration works so well. And also my colleagues from physics, Stefan Meyer. I think it was for me quite important when I started here 2 years ago that I got a very warm welcome from all the colleagues in the department, that I was also quite quickly introduced in the Center of Plasmonics, which really was pushing all our efforts very much. And my colleagues from Link Microtech, they're here in the audience. They helped me with our efforts with the company. Actually, Link Microtech, they manufacture. They are now manufacturer of our Resonator system. So I think we already organized possibly some working places in this country, at least potentially in the future. No? So I think that's very nice. And also my former colleagues from Jülich. And again, my colleagues in the Department of Materials, thank you, all of you. I think I had a very good start here, and I really very much enjoyed the almost 2 years I was working here, and I hope it will go on for a very long time. And finally, also, since my wife is not anymore in, I'd like to thank my wife and our daughter Elisa for being quite patiently listening to this very long talk. So thanks very much.